Hello, good morning friends. Welcome to our online lecture series. Today we'll be starting with the second module, which is nothing but the work and energy. In our earlier module, whose name was motion, we have discussed some of the basic terminologies and the Newton's laws of motions. There we have studied what is force and what happens if external force is not acting, and also in the Newton's third law we have studied that if force is acting on the body, what happens to that body. Now you might have a questions in your mind. Just let me ask you one question. For example, if I say that an object is there and if I am applying a force on it, okay, so we have studied that whenever the force acts on a body changes its position. Change in position of body. Change in position of body occurs, and this change in position of a body, which is nothing but a motion, and due to the motion of a body displaces from one point to the another point. Now if this force acts for a long time, okay, if this force acts for a long time, it will travel a certain distance up to the time up to which the force is acting on that body. Okay, now this force into time, that is the quantity which is called as impulse in physics. Impulse in physics. And also, as the body is in motion, as body is displacing from its position, so it is covering a certain distance, and so there will be a term that is force into displacement, which is nothing but the work done. This quantity force into displacement, that is called as the work done. Now in this chapter we will be discussing the terminologies associated with the work, and in addition to this we will be discussing what is this work, how it can be, how you can get a work from a constant force, variable force. Also we will be discussing a equivalent of a work that is called as the energy. Okay, we will be discussing energies as well. Basically we will be talking about the mechanical energies. We will be discussing about the mechanical energy. First of all, we will start with our discussion with the mechanical energy, and then we will consider one term, each term by one. Okay, so let us start with the first term, that is called as the mechanical energy. Mechanical energy. Mechanical energy is nothing. It consists of two types of energies. The first energy, that is called as the kinetic energy, and the second energy is called as the potential energy. Potential energy. So the sum of kinetic energy and the potential energy is nothing but that is called as the mechanical energy. So in this chapter basically we will be discussing with a concept of work and the mechanical energy which involves the kinetic energy as well as the potential energy. In the starting of the chapter we will be starting with the kinetic energy. Then we will move to the work done, and how this work done can be converted into a potential energy, that we will see, and based on this one we will see the law of conservation of energy in the mechanics. So let's start our discussion with the first term, that is called as the kinetic energy. Okay, so if the question, before that, if you want to know the definition of the kinetic energy, you just simply write the kinetic energy is the sum of the kinetic energy plus the sum of the kinetic energy and the potential energy. Now we will first start with the kinetic energy. First of all, we will define what is kinetic energy, we will discuss its unit, and then we will move into the more detail of the other parts. So let's start with the first part, that is called as the kinetic energy. kinetic energy. Now, this kinetic energy, you might have studied it in the lower classes as well. If some object is in motion, it has a kinetic energy. Okay, if some object is in motion, then it has a kinetic energy. So the kinetic energy can be defined as the energy possessed by a body by virtue of its motion, is called kinetic energy. So if some object is in motion, this word is very important. So due to the motion of an object, if a body is having a certain amount of energy, that is called as the kinetic energy. Mathematically, kinetic energy is given by the formula, that is 1/2 mv square, where v is the velocity of an object and m is the mass of an object. So 1/2 mv square, it is a mathematical formula for the kinetic energy. Okay, so if you want to find out its unit, and one more thing before going into the unit, let me tell you one thing, that kinetic energy is a scalar quantity. Kinetic energy is a scalar quantity. And its unit I was talking about. Basically, if you see m, which is the mass of an object, it is measured in kilogram. Okay, and velocity is measured in terms of meters per second, and its square it is there. So it is meters square per second square, and this kilogram meter square per second square, that is nothing but in SI system this is called as joule. This name has been given after the scientist Joule, which was an English physicist who worked in the 18th century. So it is joule in SI system, and the same unit in the CGS system, that is called as the arc. This is the unit in SI system, and this is the unit in CGS system. And there is a relation between the SI system and the CGS system. We will see that as well. This is joule and this is arc. Okay. Just now we said that 1 joule is nothing but 1 kilogram meter square per second square. Okay. This is in SI unit. Now we will try to convert this quantity into CGS unit. So we know that 1 kilogram is nothing but 10 raised to 3 grams. 1 kilogram is nothing but 10 raised to 3 grams, and 1 meter is nothing but 100 centimeter, that is 10 raised to 2 centimeters. Okay, so instead of kilogram I will try to convert this unit into CGS unit, that is 10 raised to 3 gram into meter. I will try to write it in terms of centimeters, so it is 10 raised to 2 centimeter, but here it is meter square. So if I square this quantity, then 1 meter square is equal to 10 raised to 2 square, that is nothing but 10 raised to 4 centimeter square. So I should be writing over here, instead of 10 raised to 2, it should be 10 raised to 4 centimeter square per second square, because in CGS and SI both the systems time unit is second only. So 10 raised to 3 plus 10 raised to 4, that will be 10 raised to 7 gram centimeter square per second square. and this gram centimeter square per second square, that is called as an arc. So it is 1 joule is equal to 10 raised to 7 arc. So this is nothing but 1 joule. This quantity which is on the LHS side, that is called as 1 joule, and 1 joule is equal to 10 raised to 7 arc. So you can have a relation over here. 1 joule is equal to 10 raised to 7 arc. You might have studied this in your lower classes as well, but it will be just recap of the whatever the knowledge which you have already gained. Okay, I hope you people have understood. The kinetic energy is nothing but the energy possessed by a body by virtue of its motion, and means if any body is in motion, then it will have a certain amount of energy, that is called as the kinetic energy. Energy due to the motion of an object, that is called as the kinetic energy. Mathematically, kinetic energy is given by 1/2 mv square. It is a scalar quantity. In SI system, it is measured in terms of joules. In CGS system, it is measured in terms of ergs. And 1 joule is equivalent to 10 raised to 7 ergs. Okay. Now we will move to the next definition, that is called as the work. So now we will go to the next term, that is called as the work. Okay, now work. Now we will be defining the next quantity, that is work done. Actually, specifically speaking, work does not have any physical work does not convey a proper meaning in physics, but if you want to convey some proper meaning, the work is always expressed in terms of work done, because it will be done on some object. That is why work is always written as work done. Okay, so now let us define work done. Work is said to be done on an object. Work is said to be done on an object. If work is said to be done on an object, if the force acting on the object, if the force acting on the object is able to move the object through a distance in the direction of the force. Okay, so when we say that work is done on an object, if a force is acting on that object and that object is displaced through a certain distance in the direction of the force. So always remember that. So direction of the force and the direction of the displacement or distance traveled, there has to be same. Means what? The force should be, the displacement should be in a tangential direction. They should not be having a different direction or perpendicular direction. If both are in same direction, then and only then we can say that there is a work done. The best example is that suppose a coolie is there, and if he lifts some luggage on his head, and if that coolie is on the same place only, there is no work done by that coolie. Okay, you might ask me the question that How is it possible, sir? Because the object, sir, that luggage has been lifted from the earth's surface to a certain height. So there is a change in the potential energy. So there has to be some work done. Remember, we are talking about the work done on an object. There is no work done on the luggage. You can imagine that as the pulley is lifting an object or luggage from the ground surface, the pulley is doing some work done on his muscles or bones, but there is no work done on the object. Remember this thing. It's a little bit critical thing. So work done on the luggage, it is zero, because there is the force is applied in this direction, in vertical direction. There is no displacement of that pulley in vertical direction. Pulley is standing in the same position. If he has covered certain distance in this direction, then we can say that there is a work done. Okay. Now let us say mathematically the work done is given by the work done is given by a scalar product of force and displacement. Okay, so the work done is a scalar quantity because it is a scalar product. So you can write this as dW is equal to F bar dot ds bar. Displacement is a vector quantity, force is a vector quantity, dot product of two vectors is a scalar quantity, which is nothing but the work done. So it is a scalar quantity. If you want to write, you can write. It is a scalar quantity and its unit. The unit of the work done is same as the kinetic energy. In SI system, it is measured in terms of joules. In SI system, it is measured in terms of joules, and in CGS system, it is measured in terms of ergs. And there is a relation which we have already seen: 1 joule is equal to 10 raised to 7 erg. Okay. Now we will prove one theorem which tells us the relation between the kinetic energy and the work done. Okay, so let us move to our next topic, that is the relation between the work done and the kinetic energy, which is known as the work energy theorem. Okay, we will be using this work energy theorem for solving the numericals in the coming lectures. Okay, so let us start with the theorem that is called as the work energy theorem. Work energy theorem. Work energy theorem. Now, this work energy theorem, it relates the work to the energy of an object. Okay, it is relating a work to the energy of an object. For that purpose, what we will consider? We will consider one object whose mass will be m and a constant force of magnitude f. It is acting on that object. We will try to calculate how much amount of work done we are getting, and then we will try to correlate this calculated work done with the kinetic energy. Okay, the scheme for the theorem, it is that first of all we will consider one object whose mass will be m. We will try to calculate the work done on that object by a constant force f, and then we will try to correlate that work done in terms of kinetic energy. Okay, so let us start with the theorem. Consider an object of mass m acted by a constant force f. Okay, So consider an object of mass m acted by a constant force F. Suppose the force displaces an object. The force displaces an object through a distance ds in the direction of the force. We had seen earlier that in order to have a work done, the force and displacement both has to be in a same direction. So for this purpose, what I am considering that force displaces an object through a distance ds in the direction of force. Okay, the work done dW is given by now we'll try to write down the work done, that is dW. Just now we in our earlier section we have considered the definition of the work done, that is a dot product of force and displacement. So it is F bar dot ds bar. We know that definition of dot product of two vector. Let us say that A bar is a one vector, B bar is a one vector. If these two vectors are making an angle theta, then the dot product of these two vectors A bar dot B bar, it is given by AB into cos theta, where A is the magnitude of first vector A bar, B is the magnitude of the second vector B bar, and cosine of the angle between the two vectors, where theta is the angle between these two vectors. So here in this case we will get F into ds into cos theta. Here we will get F into ds into cos theta. But I will write here, but F bar and ds bar are in same direction. We have already considered this thing. Are in same direction. We have written over here the direction of the displacement is in the same direction, is in the direction of the force. So as these two vectors are in the same direction, if you have two vectors in the same direction, the angle between them theta is equal to 0. The angle between them, it will be 0. From this one we will try to write down the value of cos theta, which is cos of 0 degree, which is nothing but 1. So this expression we can rewrite like this: dW is equal to F into ds. It is just a magnitude of force and magnitude of displacement. Okay. Now, according to Newton's second law of motion, Newton's second law, we had seen the Newton's second law of motion. What is the Newton's second law of motion? The Newton's second law of motion was this: force is equal to mass into acceleration. The Newton's second law of motion was force is equal to mass into acceleration. We had seen the definition of acceleration as well. What is acceleration? It is the rate of change of velocity. So I can rewrite this as m into dv by dt. So this we can write m into dv by dt. So force, it is m dv by dt. So I will write it this in this expression. Here I will write, therefore, if I substitute this value of f in this expression, dw is equal to f. What is the value of f? It is m into dv by dt into ds. This is equal to. Further, I can reorder this. I will rewrite this in this fashion: ds by dt into dv. I will rewrite. I will first of all write ds and then I will write dv. So from this one, therefore dw is equal to. Now, what is ds? It is a displacement It is a displacement and its derivative with respect to time. So by a definition of the velocity, what is rate of change of displacement? But the rate of change of displacement, rate of change of displacement is called velocity. Okay, so I can rewrite this as V is equal to ds by dt. So actually rate of change of displacement with respect to time is nothing but the velocity. So if we rewrite this value, E is equal to ds by dt is equal to, so we can rewrite dw is equal to we can rewrite m into ds by dt, that is velocity. From this expression, ds by dt is velocity into dv. It is dv. Now this is an infinitesimal displacement, so we have considered a displacement over a small interval. Suppose, let us consider that when I have applied this force, the initial velocity was u. Okay, initial velocity was u, and after applying this force, the velocity of the body has changed to v. Okay, so let us consider that. So assuming, we can write if we can write suppose application of force increases or changes, we can write changes the velocity from u to v, where we will call u as an initial velocity, v as a final velocity. Okay, then total work done is given by we can write total work done W is equal to, the total work done will be given as a integral over a dW where your velocity is changing from u to v. Okay, I'll write it over here. This total work done, it will be given by W is equal to total integral over a dW where your velocity is changing from u to v. Okay, now what is value of dW? This we can substitute from this equation. Let us call this as an equation number 1. Okay, from equation 1 we can rewrite this as u integral is running from u to v, value of dW it is m into v into dv, Now my integral is with respect to v, so m is constant, I can take it outside. In integral you will get u to v into dv. So it's just a simple power formula of integral we have to use. Power of v, it is 1 over here. So if you have this, we know this formula, integral x raised to n dx. This you can rewrite as x raised to n plus 1 upon n plus 1. Okay, so you have to increase the power by 1 and you have to divide by the same power. Okay, so here in this case the power is 1. So 1 plus 1 will be 2. So here I can write v square divided by 2, and integral was running from u to v. I'll just erase this one. Okay, so this is equal to m into, now First of all, we will substitute the upper limit. So it is v square by 2 minus lower limit, that is u square by 2. And if you separate out this term, if you multiply by m, so this you can rewrite as 1/2 mv square minus 1/2 mu square. Now see, what we have considered, it is v is the final velocity, u is the initial velocity. So 1/2 mv square, we have just seen 1/2 mv square is a mathematical expression for the kinetic energy. So you can write W is equal to kinetic energy in the final stage, final kinetic energy minus kinetic energy in the initial state. So it is initial kinetic energy. So the mathematical expression of work done, it has been reduced to, the mathematical expression for a work done has reduced to W is equal to final kinetic energy minus initial kinetic energy. So what is this? Final kinetic energy minus initial kinetic energy. This is the change in kinetic energy. This is nothing but change in kinetic energy. This is the change in kinetic energy. So what you can see, the work done on an object with a constant force is nothing but the change in kinetic energy. Now we will state this theorem of work energy. Okay, this is the mathematical expression for, this is the mathematical expression for work energy theorem. Work energy theorem. Okay. Now we will state it in the language, that is, it states that the work done by a constant force, by a constant force is equal to the change in kinetic energy of an object. So this is a statement of a work energy theorem, which states that the work done by a constant force is equal to the change in its kinetic energy. This is called as the work energy theorem. Okay, so I hope you people have understood it well. Today we have just started our second module. There we have discussed initially what is kinetic energy, then we have considered what is work done, and we tried to calculate correlate what the work done in terms of kinetic energy in the form of work energy theorem. Thank you.